So what you have here is that you have an air track. And the thing that you want to remember about an air track, which you may not know, is an air track is a frictionless system. So what happens here is that there's air. It's like an air hockey table. It's not completely frictionless, but it has very, very low friction for short distances. And so what happens here, as this thing floats over an air table, it doesn't make contact with the ground. So what you have here is a glider is essentially a thing that's going to move across this surface. So it says here that this glider has a mass of 0.1 kilograms, and it's attached to a spring of a horizontal air track by a spring force here. So what am I really talking about? Well, it says that I have a cart that looks something, I have a system that looks something like this here. So imagine that I have my system right here. How am I going to draw this? And again, you have air pushing up on this object. And what you're going to find here is that it says initially the spring is unstretched, but it's moving to the right. So I imagine that I have a spring. And what you're finding here is that attached to this thing here is my glider. And let's say that this guy's going to sport a red color today. Okay, there's my glider. And what you're seeing here is that at this point, this is the X equilibrium, which then means here is that there is no energy, no work stored in the spring. In other words, I have an unstretched spring. So there's nothing there. However, this cart is moving with an initial speed. So in other words, its speed at this point, they tell us is 1.5 meters per second. So it's moving. Okay, so let's keep reading here. So I got the glider, I have a mass. There's a spring constant to this, which we'll talk about in a minute. And then initially the spring is unstretched and the glider is moving to the right. Okay, so here we go. Determine the maximum distance d that the glider moves to the right if the air track is on. So if it's on, then that means here that this surface right here is frictionless. And that's what they mean by mu of k equal to 0. So then what's going to happen here is that this little guy here, he's going to chuck it all the way to, let's say, right here. So then he gets to right there. In other words, we know that the spring, just like we talked about before, it's going to move a displacement all the way to right there. And that's going to be its maximum displacement. And of course, this maximum displacement is the turning point. Okay, it's the turning point. So now, what do we know? What we know here is that we can sort of like try to get an idea of what's going to be happening here. So according to the work energy theorem, let's draw a bar diagram. So let's talk about a work energy bar diagram. Okay. So what do I know here? Well, I know this thing has kinetic energy. It starts off with kinetic energy. So according to the work energy theorem, what we know here is that the cart is moving at the equilibrium point. So that, let's say that we arbitrarily give it this amount of kinetic energy at this point. And this is going to be the kinetic energy at the equilibrium point, right? That's what we know. And what we also know is that eventually this cart is going to get to the point where its speed must be 0. And of course, because that's the turning point right there, that means that the kinetic energy at the turning point must be 0, because that's where it turns around. So the only way that could be true here is that there must be negative work of the spring. So if I look at negative work of the spring, if this is 3 squares, then this has to be 3 squares. And that has to be the work of the spring. So check it out. What do you think? The way I'm looking at this thing, I am doing what? I am literally solving an equation with pictures. This is what the work energy theorem does. If you try to do this with Newton's second law, you have to solve a differential equation. And it's not this clean. So this is pretty awesome, because if you solve the differential equation, what you're going to find here is you get cosines and sines. Do you see any cosines and sines here? No. Dude, this is a freaking sexy picture, if you ask me, because all of a sudden I'm doing, I'm avoiding all that hardcore mathematics, just relying on a physical picture. So let's go. We know that this spring work has to be negative. So when we look at this thing, we could come in here and we could just say, hey, I know that this has to be negative. So it must be 1/2 kx squared. That's the work. But it had to start from someplace, which is where we get our 0. Remember, work is not about 1 point. It's about 2 points. So check this out. So I'm going to go right off my picture. Right? My picture tells me that, wait a minute, this kinetic energy is going to be what? 1/2 mv squared at the equilibrium point. So from my bar diagram, I could now calculate what the maximum distance is. So now, using the bar diagram, we can calculate maximum displacement from equilibrium. So if I look at this thing, guess what I'm going to get? I'm going to look at this thing and I'm going to go, okay, what does this equation tell me? Well, if I look at the picture, note that I should be careful. There's no double minus sign here. Okay, there's no double minus sign. Maybe I should take the minus sign off right here. I'm going to take that minus sign off. And you'll see in the reason why I should take that minus sign off. So the work energy theorem then says, hey, the kinetic energy at the equilibrium point, now I put the minus sign. Why? Because it goes below. The height of this thing is 1/2 kx squared. It's going to be minus the work of the spring. And this guy is going to equal the kinetic energy at the turning point. But we know that this guy is 0. If this guy is 0, what we can do here is that this really tells us that this must be 1/2 mv equilibrium squared minus 1/2 kx squared at the turning. And then this here has to do with the equilibrium point. Maybe what I should have done in hindsight, maybe I should have written this as 1/2 kx turn squared minus 1/2 kx equilibrium squared. Work is the change. And that's why you're seeing a positive sign because then I'm going to get a minus, and a minus gives me a positive, and it looks like this. And then this guy has to be equal to 0. So check this out. So x max is equal to x turn. And if you do that, look what I'm going to do. If I take the spring term off to the right, the 2 halves cancel out. God, maybe I should do I tell you what I want to do. I just want to write the equation. But my experience is that it's better to do the algebra. So I'm going to do the algebra. Sorry about that. I don't mean to be a pain in the ass. But I'd rather you follow me. So look, I'm going to write 1/2 mv equilibrium squared. And now this is going to be 1/2 kx turn. And right away, you could see that the halves are going to cancel out. If I solve this, I got to divide both sides by k. And then I say that x max is the same as x turn. And because that's a square root, I got to take the square root of that. But note, I have that k factor, so then this should be the mass times the equilibrium speed squared divided by k. So when I'm looking at this guy, what you're seeing here is that that's my maximum, displacement. And then if I look at the problem, it tells me that the mass is 1/10 of a kilogram. It tells me that the equilibrium speed is 1.5 meters per second. And it tells me that the spring constant is 20 newtons per meter. So all I got to do is I just got to put everything into that, and then I have a distance. So if I do that, what I'm going to do here is I'm just going to give you the number. And this is the number that you get. You get 0.106 meters, or I can write this as 10.6 centimeters. And this is the maximum displacement from the equilibrium. Look at that. That is awesome. You apply this to Newton's second law. Note, what would you do in Newton's second law? You come in, you write the net force. What does the net force say? Well, that's minus kx, but this has to equal mass times acceleration. But look, I have a variable force, so now I have to go in and write a differential equation. And from this, I have to go calculate x. So then I solve this for acceleration or position, excuse me. And then I look at the equation and then I judge when is that at maximum. Dude, this is so much easier, right? Look at that. From the picture, I went here. That is so much easier. Let's go to the next part. I want to go do B now. Okay. So now we're going to look at B. So now what you do is that as this thing is, instead of, not having any friction, you now have friction. So when I look at this scenario here, we're going to do the exact same thing. So look at our picture here. So if I look at our picture, just to save a little bit of time, and I know I'm being a pain in the ass. Sorry about that. Let's look at this picture. So the picture is exactly the same. So I still start off at the equilibrium point right there, right? Now what you're going to find here is that we're going to get a maximum distance again. But check this out though. We now have sliding friction. And you could see that now I have a non-zero frictional force here. So think about this thing. So if I try to interpret what we expect here, Well, what do I know here? The spring force, we already know, does negative work. If I add friction to this problem, is friction going to reduce the kinetic energy of the car? Absolutely. So what we kind of expect here is, so if I start drawing a bar diagram right away, this is what I would expect here. Well, for starters here, let's say that I have this amount of kinetic energy. Actually, let me make this a little bit smaller because I want to try to keep in space here. So let's say that my kinetic energy here, damn it, is this amount, is 3 squares. So this is my initial kinetic energy from beforehand. Now, I know for a fact that sometime later, we're going to take it to its turning point. In other words, its final kinetic energy must be what? At the turning point should be 0. So I got to bring that down to 0 according to the work energy theorem. So what do I mean by that? Well, I know that there's work done by the spring. And I know, so if I'm looking at this thing, as this thing is moving, right, I know that the displacement is in that direction. And I know that there's a spring force going like this, but at the same time, there has to be the work of friction now. So because the frictional force is now helping the spring force doesn't have to do as much work. So what I'm looking at, if I look at what we had up here, I did green for the spring force. We should have less spring force. Let's say it's that amount, right? This should be the work of the spring. In this case here, but in order to bring this down to 0, we must have work by friction. So in this case here, let's come in and just say, yep, here's the work of friction. And if I look at the work of friction, it should be reducing it too. So there should be 2 work that are going to be negative here. Now remember, work is about what? Change. So if I look at the work of the spring, we saw that there's a negative sign here, but note it's already, we know that it's negative because it's always negative. So it should be 1/2 K from the turn to 1/2 K to the from the equilibrium. And when I look at the work of friction, this is a constant force. So if I look at the work of friction, friction should be what? The work done by friction over the displacement. But wait a minute, what do I mean by displacement? It's going to be the work of friction getting to the turning point minus where it started at the equilibrium point. So that's the 2 works that are going to have to reduce the kinetic energy. So here I go. Now that I have that, I'm going to apply the work energy term. So applying the work energy term, this implies then, I'm going to go right from my picture. So what does my picture says? Well, it says I got my kinetic energy at the equilibrium. Now I have the work of the spring being negative, and I have the work of friction being negative. And what's that going to do? That's going to change my kinetic energy at the turning point. As before, this guy is 0 here. So now let's put in our terms here. Well, x equilibrium, of course, is 0. This is 0. So now I have my turning point for this friction here. But note, this turning point should be shorter than the other one. So I'm going to be a little bit more careful. This time, I'm going to add a prime to let you know that I'm talking about a different point, not the same point. So when I look at this thing, I'm going to write my equation now. So this tells me here that this should be 1/2 mv equilibrium squared. Then my spring here, look at my spring term, I'm going to get minus, and then I'm going to get 1/2 k x prime squared for the new turning point plus 0. Then I look at my work of friction, which is then going to be my frictional force times x turn prime minus 0. And this guy's going to equal 0 because that's what the kinetic energy as the turn is here. So what you're going to see here is that now I got to go in, and what I got to do here is that I need to solve for x turn prime. So let's look what I get here. So if I look at this term here, I'm going to get a term. So look at that. This is negative. This is negative. So I'm going to take both negative terms over to the right. And then I'm going to have this constant 1/2 mv squared be a constant. So if I look at this thing here, what you're going to see here is that I'm going to get this. I'm going to get 1/2 k x turn prime squared plus, then I have my frictional term, which will be f of k x turn prime. And then I'm going to get minus 1/2 mv velocity squared. And this has to be equal to 0. So do I know all of my constants? Well, let's look at my constants. What we know here is we know that K is 20 newtons per meter, as stated in the problem. I know that the mass of the cart is 0.1 kilograms. And then check this out. The frictional force should be mu of K times the normal, but because this is a flat surface, it should be mu of K times mg.
Hey, Carlos, why is it x prime instead of x?
Because you got to go back up to here. When you come up to here, if I have a speed of 1.5 meters per second initially, and it's frictionless, it's going to stretch out some distance. Here, if I have friction now, it shouldn't go as far. And because it doesn't go as far, I have to have a different turning point now. Is that clear?
Yeah, it makes sense. Thank you.
Okay. And I just saw that somebody answered. There's two different Ks, right? When I write a K like this, that's 1/2 mv squared. If I write a script K, this guy is the spring constant associated with the spring force. So all I got to do here is that, by the way, the other thing I forgot to mention here is that the spring constant, I believe, was 4.7. So I know all of these constants. So all I got to do is I got to solve for the quadratic equation. So if I solve for the quadratic equation, check this out. I'm going to get, so solving the quadratic equation, you're going to see here that I'm going to get x turn prime should then be minus mu of k mg plus or minus, then I get b squared minus 4a times c square rooted, and then everything's divided by 2c. So if you punch these things in here, what does this really mean here? Well, I'm going to get two numbers. I'm going to get 0.086 meters, and then I'm going to get minus 0.132 meters. Well, clearly you can't have a negative value, but there is some reason. I mean, so let me be, just to be real clear, this is physically impossible. So why is this physically impossible? Well, what we really have right here, if I was to just kind of grab this guy and come back down here, note that this is an oscillatory system, right? This is an oscillation. Look, here's my oscillation. So what you're seeing here, what happened? Oh, it's just, there's a delay. What happens here is that this means that this thing is oscillating about this point here. So what should happen? Well, this cart eventually from the equilibrium point means it should also be over here eventually at some point. And what's that point, what we're measuring from? Well, it's going to be this negative 0.132 centimeters behind that thing. But we assume that this is a barrier and it can't get there. That's what I mean by it being physically impossible. It can't go through the barrier. So the only reasonable solution for this, because you can't go through the barrier, this is the real solution. So when I look at this thing, you could see that x turn prime is then going to be 0.086 centimeters, which is 8.6 centimeters. Now, does that answer make sense? And the answer is yes. Why does it make sense? Because check this out. We saw that, so if we compare to x turn with no friction, what we're seeing here is that x turn with no friction, what was that value? I think it was 10.6 centimeters. You can see that x turn is greater than x turn prime at 8.6 centimeters. And that's so not a surprise here because we assumed that the work of friction was going to stop it from going any, not as far. And that solves that example right there.